Hey everyone, welcome back. Today we are looking at Chapter 3, Acceleration and Accelerated Motion. And we're going to be looking through the different notes. And of course, like always, we'll have our additional resources at the end. So without further ado, let's go ahead and get going, shall we? All right. So acceleration. This is section 1. Acceleration, the definition of it is the rate at which velocity changes over time. So remember, velocity is speed in a given direction. So therefore, an object is considered to be accelerating if it experiences a change in the speed. So whether it is speeding up or slowing down, if it's experiencing a change in its direction, because velocity includes direction. So if it's going in one direction and then it switches, that is considered an acceleration. Or both. Maybe it slows down as it's turning. Regardless, it is a change in speed or direction, or direction. So it's a change in velocity over time. And we can look at that as the average acceleration equals delta V divided by delta T. So the change in velocity, VF minus VI, so that's final velocity minus initial, divided by final time minus initial time. Now, a lot of times we'll leave T as delta T because most of the problems that we look at, it's not going to say they start at this time and ends at this time. And they'll just say the acceleration occurred over this time. So most of the time, the equation will be written as A equals VF minus VI divided by T, or delta T. Final velocity is greater than initial velocity. So if the final velocity is greater, then you're subtracting the smaller initial velocity from the larger final velocity. This means that you were going at a slower speed and then you increased the speed. So the object is speeding up, and this means that the acceleration is considered positive because you are accelerating in the forward direction. Because remember, in physics, the positive and negative signs refer to direction, not value. If the initial velocity is greater than the final velocity, that means that you were going faster at first and then you were slowing down. So you were accelerating in a negative direction. You're accelerating backwards. It's the slowing down due to the acceleration going in the opposite direction. Hence why the acceleration is negative. We generally don't say decelerating in physics. That's more of a non-science term, but that's what we're talking about when we mean slowing down or negative acceleration. Instantaneous acceleration is the acceleration of an object at any given instant in time. Constant acceleration is the one that we're going to deal the most with. So constant acceleration is the acceleration is the same at any given instant of time. So that means that at any point in time, the item, the car, the vehicle, the person, whatever it is, will be accelerating by the same amount. So it'll be increasing or decreasing its speed by the same amount at each time interval. So the units, the SI units for acceleration are meters per second squared, or m/s squared. And the reason for this is because, remember, it's change in velocity over change in time. So the unit for velocity is meters per second, and the change in time is seconds. So as you can see here, it would be meters per second per second. And when we go through, we do all that, math conversion and whatnot, it ends up being meters per second squared. Just showing you where the units come from. All right, let's talk a little bit about motion with constant acceleration. So when we talk about constant acceleration, what we're saying is that as velocity increases, the object is going to travel a greater distance in each time interval, which makes sense because if you're going faster, then you can travel a greater distance in the same amount of time. If I am going at 10 meters per second at one point, then that means in 1 second, I can travel 10 meters. But if I accelerate to 20 meters per second, then in the next time interval, I moved an additional 20. So now I've gone 30 meters total, 10 in that first time interval, and then with my increased speed, an additional 20. So acceleration is constant if the velocity increases by exactly the same amount during each time interval. So it's when the velocity is increasing by the same amount, not that the distance traveled is the same. If you're going the same distance each time interval, then your velocity remains constant, in which case no change in velocity means no acceleration. But let's say you are accelerating by 5 meters per second squared. So you're already traveling at, let's say, maybe you start from rest and then you get pushed. So after 1 second, you went from 0 to 5 meters per second as your velocity. You're still accelerating. So the next second, you went from 5 meters per second to 10 meters per second. And then from 10 to 15 meters per second. And then from 15 to 20 meters per second. Notice how you keep increasing your velocity because you are accelerating, you are speeding up by the same amount each time. So an object moving with constant acceleration, it means that the average velocity is equal to the average velocity is equal to the average of VI and VF. So we can write that as let me get to this next part first. So this can be applied to the displacement as well. We know that delta x, so change in displacement, over delta t equals average velocity. We also know, as it just said, that average velocity equals VI plus VF divided by 2. So it's just finding the average of the initial and final velocity. So if we know that both of those equal average velocity, we can also set those equal to each other. So delta x divided by delta t equals VI plus VF divided by 2. So therefore, displacement with constant acceleration is 1/2 the initial velocity plus the final velocity times the time interval. Now, if you're not sure where that came from, in one of the, or in a few of the videos at the end of this lesson, we actually derive where some of these equations come from. So I definitely recommend checking those out. Final velocity depends on acceleration, time, and initial velocity. So in this case, if we just take the regular acceleration equation, so A equals VF minus VI over T, and we rearrange it to solve for final velocity, we see that the final velocity equals the initial velocity plus acceleration times time. Well, let's take a look and combine those two equations together. So we can substitute that final velocity equation into the displacement with constant acceleration. So here's the displacement equation. Delta x equals 1/2 times VI plus VF times delta t. What we're going to do is take that equation we just looked at, VF equals VI plus A times T, and we are just plugging it in for VF. And then we just go through and we reduce it and we get this equation for final, or for the change in displacement. So delta x equals VI times T plus 1/2 times A times T squared. Now again, if you're not quite sure how we made it from that top to the bottom, I do have a video on how we derive this in the additional resources, just to help you understand where these equations are coming from. So final displacement. We know that change in displacement, so delta x equals final displacement minus initial displacement. So what we can do is, remember on the last slide, we had an equation that solved for delta x. We can take that equation and this equation and plug them in together and then rearrange it. And that's how we get the final displacement equals initial displacement plus initial velocity times time plus 1/2 times acceleration times time squared. Again, if you're not quite sure where we're getting all this rearranged equations from, check out the additional resources. All right, final velocity. It depends on the initial velocity, the acceleration, and displacement. So we have this equation for final velocity where final velocity squared equals the initial velocity squared plus 2 times the acceleration times the change in displacement. Change in position, which is displacement. And then here are just some of the equations for constant acceleration in a straight line motion, so one dimensional or one direction. Form used when accelerating object has an initial velocity. So it's already moving at some velocity and then it accelerates from that. So again, these are equations that we talked about. Delta x, so displacement equals 1/2 times initial velocity plus final velocity times time. Final velocity equals initial velocity plus acceleration times time. Displacement equals initial velocity times time plus 1/2 times acceleration times time squared. And final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Now, if the object is starting from rest, that means it has no initial velocity. And what we have are these simplified equations. Pretty much in each one of these, anything that was VI was set to 0 because there was no initial velocity. So if this is no initial velocity, then that would just be 0 plus a times delta t, which is what we get here. So these are if the object is at rest. This is if it's already in motion. All righty, let's move on to section 3, position time graphs for constant acceleration. So constant acceleration produces a parabolic graph. Remember, when we saw the velocity, it was more so in a straight line. Even if it changed velocity, it was straight, and then it changed the angle, and then went straight again. But with constant acceleration, we tend to see these curving parabolic shapes, and that's because of the changing velocity at each point in time. So it makes sense, since the velocity is changing, that means the slope would be changing as well. So at each time interval, because of the acceleration, that means at each time interval, the velocity will be changing. So at each time interval, you'll have a different slope because of the new velocity. Sign of the acceleration determines whether the parabola is curved upward or downward. So just like before, if the line was going upward, it meant we had a constant velocity. If it was going downward, it meant we had, upward positive velocity, downward negative velocity. It's the same idea here. If we see an upward curve, like in this first picture, is curving upward, that's a positive acceleration, which again makes sense because, as you notice, it's increasing the position. So that means it's getting farther away from the starting point. So it's going to be positive acceleration, meaning they're speeding up and the acceleration is in the forward direction. If it's curving downward, like this other picture, then that means that there is a negative acceleration, which means that the object is slowing down. Again, it makes sense because if they're slowing down, then the position is going to be changing relative to the starting position. They start at this position, and then over time, they're going to be slowing down and could actually end up going backwards. The acceleration could actually, if it overcomes their velocity, could actually start not just slowing them down, but can actually cause the velocity to change and go in the backwards direction. And if you see a straight line, that means that there is no change no change in the velocity. So if there's no curve, if it's just a straight line, then that means that they have a constant velocity, which means if it's constant velocity, there's no change in the velocity, which means there's no acceleration. All right, now free fall. All right, so when we talk about free fall, we are referring to an object or the motion of an object when the only force acting on it is gravity. So we're not talking about projectiles, we're not talking about anything like that, saying that the only thing acting on it is gravity. And a lot of times when we do the calculations, we're going to do it with an idealistic perspective, meaning that these calculations are for ideal situations, i.e. in a vacuum and no air resistance. Now, for the most part, if you're doing it in the still air of a classroom, the air resistance is going to be almost negligible. So it's not going to have that big of an effect, which works out nicely for us. So we're not going to worry about air resistance when we calculate free fall. So free-falling objects undergo constant acceleration. So as we see in the picture here, this guy is letting go of the ball. Now, once his hand has let the ball go, the only force acting on that ball is gravity. So gravity is going to be pulling it in which direction? Downward. So it's going to undergo the constant acceleration of gravity in a downward direction. The velocity will increase by the same amount in each interval, meaning that whatever the change in velocity is here is going to speed up by that same amount here. It's going to speed up by that same amount here, then here, then here. So at each time interval, even though only 1 second passes in between each of these pictures of the ball, notice it's getting farther apart. And that's because the ball is speeding up, it's accelerating. So it's going faster at each point in time, which is why it's able to travel farther. Over here, they're showing you the velocity relative to the time at each point, which we'll get to that in a little bit. So gravity. The average gravity or acceleration due to gravity is about 9.8 meters per second squared. Now, the reason why we say that's the average is because it might change very, very slightly between your location. And I don't mean like this room of my house versus another room in my house. I'm talking about like at sea level in one state versus on the top of a mountain in another. But again, on average, we can say it's about 9.8 meters per second squared. Now, don't forget, gravity pulls in which direction? It pulls down. So therefore, it is pulling in a negative direction. So we would actually say that the acceleration due to gravity would be negative 9.8 meters per second squared. Because again, it's pulling downward. So that negative sign is simply showing you the directionality of the acceleration. We said an upward motion would be positive, which means the downward motion would be negative. So if you take a ball and you throw it up, we can both agree it accelerates, we can all agree it would accelerate upwards. It would slow down, it would stop momentarily at the very, very peak, and then it would accelerate downward while speeding up. When does the ball begin to have a downward acceleration? Well, the answer to that is as soon as you throw it up, because even though it accelerates upward, don't forget, acceleration is just a change in velocity. As soon as it leaves your hand, now the only thing acting on it is gravity. And that's why as it's being thrown up, it slows down. So if I take this is my little neck pillow, if I throw it up, as soon as it leaves my hand, it immediately starts slowing down until it reaches the peak, at which point it'll pause. So it'll have a fraction of a moment where it is at zero velocity. But then it changes direction and it starts coming downward and it starts speeding up. So that's kind of what we're talking about with this up and down throw. So free falling objects always have a downward acceleration. Now remember, downward acceleration does not mean that it is less. It means that the acceleration is being pulled down. So in the terms of gravity, as soon as it leaves my hand, as soon as this leaves my hand, gravity is going to start acting on it and pulling it down, which is going to cause the neck pillow to slow down. Even though I threw it up, it's going to start slowing down because it is a negative acceleration. It's pulling it down. It's pulling it opposite the direction of its motion. So the motion might be going up, but the acceleration is going down, which is why it starts to go at a slower velocity until it stops and then it starts going downward. At that point, the direction is downward, the acceleration is, it's moving downward, the acceleration is downward, so it's going to cause it to start speeding up. When the direction of motion is the same as the direction of the acceleration, the object speeds up. If the direction of motion is opposite that of the acceleration, it's going to slow down. So the only thing changing would be the position and magnitude or direction of the velocity. It's the same acceleration, negative 9.8 meters per second squared. But its position changes because I threw it up, and then it keeps moving up, and then down, 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 down. And the velocity is going to change as well because, well, that's what acceleration is. Upward motion. So when you throw something upward, it has a positive velocity, but a negative acceleration. So because positive velocity, negative acceleration, notice how they're opposites each other. What this means is that the object is going to move up, but with a decreasing speed. It's slowing down. Then it reaches the peak. The peak is the very, very top of the path. At this point, velocity has decreased to the point where it is now zero. It comes to a rest for a fraction of a moment. It stops for a fraction of a moment. And then it experiences the acceleration downward. In which case, we now have the downward motion. So it's being pulled down to earth with negative acceleration. And since it's now moving downward and the acceleration is downward, notice how they're both going in the same direction at this point, the object is going to be speeding up. This can result in greater displacement per time interval because since it is speeding up, it can travel farther distances in the same amount of time. All right, let's talk about those additional resources. So Science in Pajamas are the ones that I make myself. We have one on just a review of acceleration. We have one on acceleration practice problems. We have one on how we actually derived the final displacement equation. So this goes through and shows you how we get that equation. Where did it come from? And then we also have one where we derive the final velocity equation. So both those equations, where I told you that there will be a video to show you how we got to that point, how we used our existing knowledge to create that equation. That's what both of these videos are. They're just showing you how is it, the step-by-step process of how we got from the equations we know to these equations. And that's more so for your knowledge, so that it doesn't just like, poof, the equations happened out of thin air and magic. And then we also have some free fall practice problems as well. So we'll go through step by step how to solve some of those questions. Then we have other videos. We have don't memorize, what is acceleration? We have few school acceleration. We have organic chemistry tutor, kinematics in one dimension. So that's one dimensional motion. Khan Academy, acceleration versus time graphs. We have Fuse School, gravity and free fall. And we have organic chemistry tutor, free fall, physics problems. All right, I'll post a link for this presentation into the video description so you have access to the links for the additional resources. But in the meantime, you guys, I hope that helps. Definitely check out some of those videos. Or the ones I make them with the point of helping you when I'm not around. And the other ones are good additional resources to further explain what we're discussing. But in the meantime, you guys, if you have questions, hit me up in our Google Classroom, in our an email, in class, and just stay awesome and safe, you guys. I'll talk to you next time. All right, you guys, take care. Bye-bye.